All right, let's jump right into the incredibly fascinating world of manufacturing at the absolutely smallest scale imaginable. Welcome to today's Explainer. We're going to be exploring the invisible factories that literally create the foundation of our modern tech. We're talking about nanomaterials, structures so astonishingly tiny, they actually operate by a totally different set of rules.
But before we get into the nitty-gritty of how it's done, I want you to ask yourself a question. How do engineers actually build structures that are completely invisible to the naked eye? Like, we aren't just talking about making things a little bit smaller here. We're talking about manipulating matter down at the atomic and molecular levels. How exactly do you construct something when your building blocks are literally atoms?
To answer that, we're going to break down the two main opposing paths to creating nanomaterials. First, we'll look at the nanomanufacturing challenge as a whole, then explore the top-down sculptors method, followed by the bottom-up architects method. After that, we'll compare the two approaches head-to-head and wrap up with some real-world nano applications.
So let's start with part one, the nanomanufacturing challenge, or building at the impossible scale. Looking at the big picture here, the creation of nanomaterials is quite literally split right down the middle into two fundamentally opposite philosophies. You've got the top-down approach, taking bulk material and forcing it down to the nanoscale. And on the flip side, you have the bottom-up approach, where you start with individual atoms and molecules and assemble them into nanostructures. Pretty much every single smart device you use today relies on a choice made between these two very distinct pathways. Let's move over to part two, top-down, otherwise known as the sculptors method, carving down to the nanoscale.
So, just like a sculptor chipping away at a massive block of marble to reveal a statue hidden inside, this method reduces bulk materials down to the nano level. You start with something you can actually hold in your hand, a macroscopic piece of material, and you hit it with intense physical, chemical, or even radiological processes. Basically, you are aggressively destroying the bulk of the material just to leave behind the microscopic features you actually want.
The workflow here is crucial to understand. Step 1, you always start big with bulk material. Step 2, you aggressively remove what you don't need through patterning and processing, things like etching or milling. And step 3, you just keep refining and refining those patterns until you hit those perfectly carved nanoscale structures. It's essentially an exercise in extreme subtraction.
But instead of chisels, our nanosculptor uses light, electrons, and sometimes just pure brute force. Take photolithography, for example. It uses UV light cast through a mask to pattern or resist and etch a substrate. Or electron beam lithography, which takes it a step further by using a highly focused electron beam to write nanoscale patterns directly. And if you just need raw nanopowders, well, you'd use ball milling. This is where the high-energy impact of metal balls literally grinds a bulk solid material down into dust at the nanoscale. Pretty intense, right? Now, while this method is highly precise and honestly perfectly compatible with our current massive microelectronics assembly lines, there's a huge catch. All that chipping away at a block inherently creates a significant amount of material waste. Plus, it causes surface defects, impurities, and lattice damage. Basically, the actual atomic structure gets bruised in the process. And maybe most critically, this sculptors method hits a hard physical wall, getting reliable features below about 10 nanometers, which, by the way, is just a fraction of the width of a single virus, becomes exponentially difficult.
Moving on to part 3, bottom up, or the architect's method, assembling from the atoms up.
So, instead of carving down, this approach is a lot like building with microscopic Lego bricks. You start with absolutely nothing but atoms and molecules. Then, through precise chemical or physical interactions, you coax them into assembling themselves into highly organized nanostructures. You're literally building matter from the ground up.
Notice how this workflow perfectly mirrors our previous steps, but in reverse. We don't start with a bulk solid. Step 1 is starting with precursor atoms or molecules. Step 2, we introduce a catalyst or a specific environment that causes nucleation, which just means they start clustering together in a process of self-assembly. And step 3, those clusters experience controlled growth and assembly into the final nanostructured material.
To build from the bottom up like this, engineers have to use some incredibly complex and fascinating chemistry. Take chemical vapor deposition, or CVD. Here, gaseous precursors are pumped into a chamber where they decompose on a heated surface to literally grow thin films or carbon nanotubes right before your eyes. Then there's sol-gel processing, where a liquid solution transitions into a sol and then into a gel to yield highly specific porous materials or nanoparticles. And my personal favorite? Molecular self-assembly.
This is where molecules are designed to spontaneously organize themselves using weak, non-covalent interactions, kind of like tiny molecular magnets. It's almost like magic, just watching materials build themselves.
Now, because you only use exactly the atoms you need, the advantages are huge. You get incredibly high purity, extremely few structural defects, and highly energy-efficient synthesis with virtually zero material waste. You basically have ultimate control over the size and shape of your creation. But what's the downside? Well, trying to control these complex chemical kinetics on a massive factory-sized scale is incredibly difficult. Achieving that long-range order over really large areas is still a monumental challenge for engineers today.
Which brings us to part 4, comparing the two approaches, a head-to-head analysis.
When we put these two approaches head-to-head across every major category, the contrast is super stark. The top-down approach is all about reducing bulk materials, which leads to functional but often imperfect, defect-prone materials that we primarily use for things like microprocessors and computer chips. Bottom-up, on the other hand, is all about assembling atoms and molecules. This yields breathtakingly pure, crystalline structures with way fewer defects, making them perfect for things like nanotubes, quantum dots, and drug delivery carriers.
And this fundamental difference totally dictates their starting states. Top-down absolutely demands a solid starting block, right? You can't carve a gas. You need a physical, solid chunk of silicon or metal to start etching away at. Bottom-up, however, inherently relies on the fluidity of liquids and gases. You absolutely need those atomic precursors to be highly mobile, so they can freely interact, nucleate, and self-assemble into complex structures.
Finally, part 5, real-world nano applications, where the invisible meets the everyday.
So with all this talk of invisible factories, molecular Legos, and electron beams, you might be wondering, why does all this actually matter to your everyday life? Well, it matters because this tiny world completely runs our giant one. The carved-down, super reliable precision of top-down manufacturing gives us the integrated circuits, the MEMS devices, which are basically microscopic mechanical sensors, and the microelectronics powering the very device you're using to watch this explainer right now. Meanwhile, the high-purity, assembled nature of bottom-up synthesis makes next-gen tech possible. Things like brilliantly colorful quantum dot displays, insanely strong carbon nanotubes, and highly targeted, life-saving drug delivery systems.
What you really should take away from this whole explainer is that neither method is entirely better than the other. They are absolutely essential complementary halves of the modern nanotechnology revolution. Top-down excels at complex, large-area architectures like computer chips, while bottom-up completely masters the art of flawless material properties and atomic precision.
But here's something to chew on as we wrap up today. Remember that 10-nanometer physical limit of the top-down sculptor's method we talked about earlier? As consumer demands for faster, smaller, and more powerful tech keep pushing us right past those physical limits, it really leaves us wondering, when the chisel is finally too big to carve the stone, will the future of our most advanced technology inevitably have to be built entirely from the atoms up? Thanks so much for learning with me today.